now that we know how to find the derivative using the formal definition, also known as the limit process, we're going to start talking about ways to find derivatives without limits. So the first thing we need to talk about is the constant rule. The constant rule states that the derivative with respect to x of any constant always equals 0. That should make sense to you guys, because if you think of a constant function, what's its shape on a graph? Like if I have a constant function y equals 7, what shape is that? What kind of line?
Straight.
All lines are straight, but what kind of line?
Vertical.
Y equals 7.
Horizontal.
Y equals 7 is a horizontal line, right? Well, what's the slope of any horizontal line? 0. So any constant function takes the shape of a horizontal line, and the slope of any horizontal line is 0, and therefore the derivative of any horizontal line is 0. So the derivative of any constant is 0. So if we're asked to find the derivative of y equals 7, we simply state that y prime equals 0. Another notation we could use for that is that dy dx equals 0. What if I have f of x equals 7? What's the derivative?
Would be undefined, since it goes straight up.
F of x equals 7 is the same as y equals 7, right, you guys? It's still a constant. The only thing that changes is our notation. F prime of x equals 0. Or the derivative of f with respect to x equals 0. How about a function that states that s of t equals -3?
0.
S of t equals 0.
S prime of t equals 0. Still a constant. There are no variables involved in this. Therefore, all of these derivatives should be 0. I also want to point out that when your book uses k, it is not a variable. If we have y equals k times pi squared for part D here, k is not a variable, it's a constant. It just means any constant coefficient. So if we have y equals k times pi squared, is pi squared a variable? No, it's also a constant. So even though it doesn't look like it, the derivative of y equals k pi squared is still 0.
It's just a number times a number, which is still a number.
Right, just a number. So if all you have is a number and you're trying to take the derivative of that function, then the derivative is always 0.
Is there another way to write the formal notation of that?
No. I don't understand. So notice that all of the derivatives are 0, but there are multiple ways that you can write the notations. We typically prefer, because they're easier not only to write but to type and they don't look like fractions, we typically prefer these notations, but you can also do them in the derivative of your dependent variable with respect to your independent variable. So it just depends, that changes each time. So for s of t, that would be ds over dt, and for y's, that would be dy dx. We're assuming that that's an x there. We actually don't know. You know, for this one, we have no idea really what our independent variable was because we don't have it. So we typically just assume that's an x when there's a y there. Now we're going to talk a little bit about the power rule. The power rule states that if n is a rational number, then the function f of x equals x to the n power is differentiable, and the derivative with respect to x of that function will equal n times x to the n minus 1. So that's the power rule. The power rule will change your life. So in words, what that means is that if you're trying to take the derivative of x to some power, you can always do that by taking the power, we're calling it n, bringing it down to the front and making it the coefficient, and subtracting 1 from the power. Got it? You can take the power, bring it down to the front, make it the coefficient, and subtract 1 from the power. So let's look at these 3 examples. We have the function f of x equals x cubed, and we want to find the derivative. And we actually did this one in one of our homework problems last time. Right? We actually talked about it just a few minutes ago. We did it. What did we get when we took that derivative? We got 3x squared. Here's why it works without the limit, or how it works. without using the limit. Because it is a power function, it is simply a variable to a power, you can apply the power rule. You take the 3, you bring it down in front, you subtract 1 from the power, and that's your derivative. A lot easier than the limit process, wouldn't you say?
I would say so.
I would say so too.
I agree.
Alright. So then, if you want to look at a radical function, such as g of x equals the cube root of x, you first have to write it as a power function instead. So anytime you have radicals, you're going to need to rewrite those in exponential form. That's why we spent all of that time in Algebra 2 torturing you with radicals and exponentials. So you can't take derivatives from radical form, but you can always rewrite the radicals as exponents. So the cube root of x is really x to the 1/3. So now we see it as just a variable to a power. And even though that power is not an integer, you can still apply the power rule. And you can say that the derivative of g with respect to x, or g prime of x, equals, bring the power down, 1/3, subtract 1 from the power. What is 1/3 minus 1? Negative 2/3. You will get really good at subtracting 1 from fractions over the course of this semester. Do y'all know a quick way to subtract 1 from a fraction? You do top minus bottom, keep the bottom. To do 1/3 minus 1, you say 1 minus 3 is negative 2, and you keep the bottom. That's a quick way. Any fraction you can subtract 1 from by doing top minus bottom and then keeping the bottom. Okay, now here's the problem with radicals. A lot of times you end up with negative exponents, and even though you are now allowed to leave radicals in the denominator, you are not allowed to leave negative exponents ever. I insist that you rewrite them as positive exponents, and so therefore we'll drop them into the denominator. If I want to rewrite this, I will have 1 over 3x to the 2/3 power. Does that make sense to you guys? Mm-hmm. If you have a negative exponent, you can drop it into the denominator and make it a positive exponent. Okay? And then, typically what we require of you is that you take it back to the original form. If I originally gave it to you as a radical, then it is expected that you return it to radical form. So that could be rewritten as 1 over 3 cube roots of x squared. You don't have to simplify the radical and you don't have to rationalize the denominator, but you do have to return it to radical form. And the only way to do that is to first get that exponent positive again. So we'll pause right there and see if anybody has any questions. For the third one, we have y equals 1 over x squared. In order to use the power rule, you have to see it as a variable to a power. So I need to figure out a way to rewrite 1 over x squared as x to some power. So first we need to rewrite it as x to the negative 2. Do you guys understand that? You move something from top to bottom and it changes the sign of its exponent? Okay. Once you see it as a variable to a power, you can apply the power rule and find the derivative. Y prime, or dy dx, equals power, bring it down in front, subtract 1 from the power. So what's negative 2 minus 1? Negative 3. All right? So technically, the calculus is done right there. We've applied the power rule, right? All that's left is to clean it up algebraically. You are not allowed to leave negative exponents. I always want you to return them to their positive state. So we have negative 2 over what? X to the 3rd. If we had done this problem with the limit definition, this would have been one of those where we substitute the limit as h approaches 0, 1 over x plus h quantity squared minus 1 over x squared all over h. And it would have been one of those complex fractions. I mean, think about how much easier it is just to apply the power rule. So from now on, unless it specifically states that you have to use the limit definition or the formal definition, you are allowed to do the shortcut in any derivative you find. For this example, we want to find the equation of the tangent line to the graph of the function f of x equals x squared when the x value is negative 2. So let's just get a visual on what we're trying to do here. I'm trying to take the parabola y equals x squared And I'm trying to find the equation of the line that is tangent to it when x is -2. So I am looking for the equation of that line right there, basically. Okay? Alright. To find the equation of any line, we need a point and we need a slope. Now, I wasn't given a point, but I was given an x value, and I can use that x value to find the point, right? So, if I rewrite this as a point, what does it become? -2, 4. So I have a point. Now I just need a slope, and I can find the slope by using the derivative, right? Okay, so if I find the derivative of the original function, I have f prime of x equals what? What's the derivative of x squared?
2x.
2x. To the what? The first power. So 2x. And then I can substitute in the x value of the point I was given. And I can find the slope. So the slope equals what? -4. So here's the slope I want. Here's the point I want. So now I can use point-slope equation to find the equation of the tangent line. So we have y minus y1 equals in parentheses x minus x1, close the parentheses. A lot faster than using the limit process. So we have y minus, we found the y value to be 4 at that ordered pair, equals -4, parentheses, x minus -2. So we have y minus 4 equals -4x minus 8. So y equals -4x minus what? 4. Right? Yes? Okay. That's the answer to the problem. So apparently, if we continued this line down, it would cross right there at -4. So, kind of makes sense to us. Like, you should be able to visualize it, and if you look at your graphing calculator, you should be able to look at the original and the tangent line, and you should see that they intersect at the point -2, +4.